Let's talk now about how we apply orbital theory to more complex molecules. Specifically, we need to talk a little bit about orbital hybridization because it's a useful model for understanding bonding in most organic molecules. To do this, we're going to use methane as an example and review some of these concepts from general chemistry. From general chemistry, we typically assign hybridization states based on the count of the number of electron domains. If we look at the carbon in methane, this carbon has 4 electron domains, which we should remember is associated with tetrahedral geometry, which we also should remember is associated with an sp3 hybridization state. The thing we need to review for this course is what exactly does it mean to have something be sp3 hybridized? So let's just redraw methane with the appropriate geometry. Remember, this is how we draw a tetrahedral atom. What I've tried to show here are the 109.5 degree bond angles between each carbon-hydrogen bond. In order to see why we need hybridization state, the question we can ask here is which orbitals does each atom in this molecule have available to it to form these bonds? Well, each of the hydrogens uses their spherical 1s orbital to form a new bond. Carbon, on the other hand, has access to the 2s and the 3 2p orbitals. So if I was to draw a picture of the carbon, I'd have my spherical 2s orbital, a 2px orbital, a 2py orbital, and a 2pz orbital that I can use to form bonds with. Now, since this drawing is a little bit messy, I'm going to simplify it a bit by showing the p orbitals as double-headed arrows. Just like we saw before, these arrows show the lobes of the p orbitals. Now, the question I have is, if we look at this picture, how on earth do we get a tetrahedron from this picture here? What this picture implies is two things that are incorrect about what we know about methane. The first being that we see a bunch of 90 degree bond angles, not 109.5, and that one of the orbitals of hydrogen should have to overlap with the s orbital of carbon rather than the p orbital, meaning one of these bonds should be shorter than the others. The way we get around this is with hybridization. We take our old atomic orbitals and we mix them to create new atomic orbitals that happen to point in the correct directions. So here is a picture of our original electron configuration for our carbon atom. Since we need 4 bonds, what we'll do is we'll promote an electron to one of the 2p orbitals so we have 4 half-occupied orbitals. This means that we can now form 4 bonds. Then what we're going to do is we're going to take the s and the p orbitals and mix them to create a new set of 4 atomic orbitals that happen to point in the direction that I want. Since we have mixed 1 s orbital and 3 p orbitals together, we call these new orbitals sp3. Now, if we think what these orbitals are like, we can imagine 4 chunks of clay. Here I've labeled one of them red and I've labeled the other 3 blue. Imagine that the red represents the s orbital and the blue represents the p orbitals. What we're going to do is break these things apart and mix them together uniformly, then combine them to create 4 new orbitals. These new orbitals have characteristics derived from their parent orbitals. Specifically, these orbitals are about 1/4 like an s orbital and about 3/4 like a p orbital. Notice in the diagram above that the sp3 orbitals are much closer in energy to the p orbitals than the s orbitals because they have more p character. These orbitals are also going to be oriented at 109.5 degrees. We can use the same process to imagine making the sp2 and sp hybrid orbitals. Now here I'm going to assume we're starting with a carbon again, which means our initial picture looks the same in both cases. We start out with a carbon with its initial ground state electron configuration, and we've promoted an electron to the upper orbital to be able to accommodate 4 bonds. If we take a look at the sp2 hybrid, what our directions tell us here is that we need to mix the s orbital with 2 out of the 3 p orbitals. This means that we're going to be creating 3 new hybrid orbitals, which we're going to be labeling sp2. We also have an unhybridized p orbital that we've left alone. If we look at the characteristics of these orbitals, they'll be about 1/3 s and 2/3 p. For the sp set, we do the same thing. We mix the s orbital with one of the p orbitals, creating 2 new sp hybrid orbitals and leaving 2 p orbitals unhybridized. These orbitals would have 1/2 s character and 1/2 p character. Now, you'll have to believe me in terms of the orientation, but in the sp2 hybrid case, we end up with the 3 hybrid orbitals oriented at 120 degrees, giving us the expected trigonal planar geometry, and the sp orbitals will be oriented at 180 degrees, giving us the expected linear geometry. So let's draw a picture of these new orbitals. What exactly do they look like? Well, they all look about the same. They look a lot like a p orbital, but with one big and one little lobe. All the hybrid orbitals look like this, but the relative sizes of the lobes are different. Since it's not really practical to draw these to scale, we're going to draw the sp, sp2, and sp3 orbitals like this, even though the lobes are slightly different sizes. If we go back to molecular orbital theory, we can also draw a picture of the bonding orbitals that use the hybrid orbitals as well. So if we imagine a CH bond, carbon is donating a hybrid orbital to the new molecular orbital, while hydrogen is donating an s orbital to the new molecular orbital. Here, since I care about the bonding orbital, I've shown these both in phase. Our new bonding orbital would look like this. Since it's symmetric along that axis, this is going to be a new type of sigma bond. Go ahead and try drawing the carbon-carbon bond between two hybrid orbitals using this same process. Pause the video here and then you can check your work with mine when we resume. Using the same process, we would take a hybrid orbital and we would mix them using their large lobes in phase to create yet another type of sigma bonding orbital. These are the types of sigma bonds that we're going to see most commonly in organic chemistry. When we see multiple bonding in molecules is when we'll need to use those unhybridized p orbitals. As we'll see in a moment, multiple bonds are built by having a combination of sigma bonding orbitals and pi bonding orbitals. The easiest way to imagine a complex molecule being built is to imagine atoms like Legos. For example, this is what the orbitals look like for my sp2 hybridized atom. The hybrid orbitals I've shown here in blue. These are my three sp2 hybrid orbitals oriented in a trigonal planar geometry with 120-degree angles. The red is my unhybridized p orbital. Now, in order to simplify my drawings a little bit, I'm going to use a shortcut that we've seen before. I'm going to represent my p orbital as a red double-headed arrow and the hybrid orbitals as a single arrow like this. In order to show geometry, I'm going to use the wedge and the dash notation to show the hybrid orbitals coming in and out of the page. So this is my building block, this is my piece if I have an sp2 hybridized atom. How about the sp hybridized atom? What I'd recommend doing here is pausing the video and looking in the book to see what the sp hybrid atom looks like with the lobes shown properly. Then come back and sketch the sp atom using the same shorthand notation that I have for the sp2 atom. I'll wait a moment for you to do this, then we'll check our work together. So based on the picture in the book, the sp atom would start with an atomic nucleus like this. Then we can add two perpendicular p orbitals. Here I've shown them aligned along the y and the z axis. Then we can add our hybrid orbitals, which are oriented at 180 degrees to one another. Now note the color coding here. These are two separate hybrid orbitals, not another p orbital. We should always have 4 orbitals total no matter what we do with any of these atoms. So how do we actually use this to make multiple bonds? Well, let's take a look at this molecule here, which is ethylene. This is the simplest possible molecule with a carbon-carbon double bond. And this molecule here, which is acetylene, the simplest possible molecule with a carbon-carbon triple bond. To start out, we need to know what orbitals are available, so we need to assign the hybridization states of the atoms in the bond in question. Here, both of the carbon atoms in ethylene are sp2 hybridized, and both of the carbons in acetylene are sp hybridized. Once we have the hybridization states, we can draw a picture of our atoms using the building block method that we've talked about in the previous slide. Here are my two sp2 hybridized atoms, and I've copied them identically here so that we can see how to put them together. Now what we're going to need to do here is we're going to need to reorient these atoms so that the hybrid orbitals are pointing at each other. So I'm going to take the atom on the right here and I'm going to rotate it so that 2 of the sp2 orbitals are pointed directly at each other. The reason I've done this is that when the orbitals are aligned like this, they can now form a sigma bond. So here I've shown the lobes, the actual shape of the sigma bond in between the two atoms. So that's 1 out of our 2 bonds for our multiple bonding domain between the carbons. The other type of bond we form is due to the 2 p orbitals being aligned with each other in parallel like this. This forms an orbital that does not have cylindrical symmetry, so we have to give it a different name. This is an example of a pi bond. So if we look at the bonding domain between the two carbons, it's going to look like this. A central, strong sigma bond in between the two atoms, and a second, weaker pi bond above and below the axis defined by the two atoms. If we really want to finish the picture, we can show our hydrogens forming additional sigma bonds to the carbons on the end like this. Practice this to see if you understand. Try taking our picture that we drew for the sp atoms in the previous slide and drawing the triple bonding domain between the two carbons by using those things as building blocks. Pay particular attention to where the pi bonds are. Pause the video here and take a moment to do this, then we'll come back and check our work together. Okay, let's take a look at the triple bond. So we would start as before with two sp hybridized atoms like this. If we look at this picture, we can see that the two hybrid orbitals are already oriented towards each other, which means we can make a sigma bond between the two atoms. We also have the py orbitals, which are aligned properly to make a pi bond above and below the axis between the two atoms. In addition, the pz orbitals are also aligned in order to make an additional pi bond. So if we look at what the triple bond looks like, it's a core sigma bond with an additional pi bond with an additional pi bond for 3 molecular orbitals representing the triple bonding domain. We also have the two hydrogens bound to the other hybrid orbitals on the outside, so this would be a complete orbital picture of acetylene. If you want to see what the lobes of the orbitals look like, see your book for a very nice picture of this. Next, we're going to be taking a look at how to use this to predict the geometry of large complex molecules.